Okay, so I hope you guys understand how these things work, okay? Now, a lot of these questions are easily answered because we had this table here, okay? But the table might not always be given to you, okay? Or maybe the table is incomplete. All right? Can we still answer if I did this, can we still answer the same questions? Okay? And the answer is yes, we should still be able to answer the questions. Now, it might be a little bit tougher, and we do have formulas that we can use for probability. And I always hesitate, okay, because I always put these formulas down, and people, I don't want you to think that formulas are magic, because they're not, okay? They're just guidelines or reminders, but the key is always understand the concept, the underlying concept here, okay? So when we said, what's the probability of small and large, we knew the answer was 0 because what? Because there's no overlap. You can't have a shirt that's both small and large, okay? Now, I'll write the formula down, okay? So what this is small and large. This is not a formula, this is a definition, and you do need to know this definition, okay? Small and large are mutually exclusive. Okay, or also known as disjoint events. Okay, what does it mean to be mutually exclusive? It means the two things cannot happen together. Okay? Okay? If a shirt is small, it cannot at the same time be large. Okay? So are there things that are mutually exclusive? Now, maybe not all of you are familiar with a deck of cards, but if a card is a diamond, it cannot at the same time be a club. Okay? So if it's diamonds, it cannot at the same time be clubs. Diamonds and clubs are mutually exclusive. Okay? So the probability of, so if we have generic labels, okay, if A and B are mutually exclusive, then probability of A and B equals 0. Alright. However, if A and B are mutually exclusive, the probability of A or B, what is that? No. No. How did we get that? So if A and B are mutually exclusive, no, you guys are just shouting things out that don't make sense. Okay? It's not a complement. There's nothing here about complements, okay? A or B, this is the, how did we get, if I said A plus B, probability of A plus the probability of B. It's not A plus B, but it's probability of A plus the probability of B. Okay? Right? What's the probability of being small or large? We took the probability of being small, and we added the probability of being a large shirt. Okay? So you should have this in your notes, and you should make an association between the result we got there and maybe the formula here. Okay, that's the only way formulas work. Okay, otherwise you're going to see this and confuse yourself. Maybe. Some of you will be fine, but All right, is that okay? Can I erase this?
No.
No, wait. Yes.
Sorry, is there a way to know the overlap if there's no table though? But like,
Yeah, you know what? Maybe I'll give you some of the overlap numbers, okay? Okay, on the other hand, maybe we don't have, so if I said probability of blue and medium, okay, blue and medium are not mutually exclusive, and so this is equal to the probability of blue plus what? Probability of medium, and then what?
minus medium blue.
Oh, I'm sorry. Oh, I screwed this up. This is blue or medium. Blue or medium. Please make that distinction. Probability of blue and medium. Okay. So if I told you probability of blue is equal to 100 out of 300, and probability of medium is equal to 80 out of 300, and probability of blue and medium equals 20 out of 300. Answer that question then.
So
Yes.
PR can also be P, or
Yeah,
it's two
P and
different-
PR, I guess they're interchangeable when they're expressing the probability of an event. Yes.
So it's probability blue plus probability medium minus. Why was the minus there? Sorry.
Because that's we're double counting it, right? If this 100 is this entire row, including the blue medium shirts, this 80, which is probability of being medium, includes the blue medium shirts, which we are double counting. So we got to subtract that out. Okay. Again, did this make sense when I did 80 plus 100 minus 20?
Yeah.
If that makes sense, stick with that, okay? Just make sure you got it in your head. Sometimes, I mean, the formulas are good, but if you're... Sometimes they can also be confusing, okay? But they are useful, and I think you should know them, but...
You said the formulas are good for when you don't have all the numbers that are in the chart.
Yeah. So sometimes we don't even give you a chart. Okay?
But we'll always get all the numbers, or will the numbers?
Yeah, so maybe some numbers are missing. Okay, so let's say okay, a store I don't know, sells apples. Okay, so we'll say we sell candies. So apple flavored candy, okay. Cherry candy, and what else? Strawberry candy. Huh? Okay. So let's just keep, let's say there's only 3 flavors available, okay? Only 3 flavors. Okay, let's say the probability of drawing apple, 0.42. Probability of cherry is 0.47, okay? What is the probability of drawing strawberry? Okay. Let's say some of the candies are round and some are square. Okay? So candies are either round or square. Okay? Those are it. Okay. Let's say the probability of drawing an apple candy that's round is equal to 0.23, and let's say the probability of all round candies is 0.60. Okay. So what's the probability that a candy is apple or round? .79. Are we not getting that?
No.
Okay. So how do we get? Is apple and round, are they mutually exclusive or disjoint? Apple and round, are they mutually exclusive?
No.
No. How do I know they're not mutually exclusive?
Just 0.23 are apple and round.
Because 23% of candies are apple and round, okay? If they're mutually exclusive, an apple candy cannot be round, okay? So that means I would have 0 there. So probability of apple or round, this would then be what? How would I get this? This would be probability of apple plus probability of round minus probability of apple and round. So I get 0.42 plus 0.60 minus 0.23, 0.79. If you just did 0.42 and 0.60, you'd get over 1. And we know that that's impossible.
Where did you get that?
Huh? What's the probability of drawing a square candy? So probability of square, this is the same thing as probability of not round, right? We said these are the only 2 possibilities. So this would be 1 minus probability of round, which is 0.60, 0.40. It's the probability that a candy is round or square. 1. Right? If it's round, 0.6. Square, 0.4. You add those 2 together, 1. We add those 2 together because they're complementary. complements, they're mutually exclusive. We just add them together. Okay? And we don't have anything to subtract away because there's no overlap. Okay, let's try something a little tougher. Okay, if I draw candy and I know it's an apple flavored candy. If I draw candy and it's apple flavored. What is the probability that it's round? That it's also round. Do we know? What's our answer? The answer? 0.548. Who got this? Good job.
Can you explain?
Yeah, of course I'm going to explain. Here's the answer. Have at it, guys. Okay. What percentage of my candies are apple flavored? 42%, okay? So, imagine I've got all these candies, right? But I've drawn one, okay? Once I tell you this candy is apple flavored, you've eliminated a whole bunch of candies already, right? Now we're only left with just this subgroup of apple flavored candies, yeah? Of the apple flavored candies, how many are round?
0.23.
0.23, okay? So there's a total of, so 0.42 are apple flavored, and 0.23 are apple flavored and round, are apple and round, okay? So if I know I have an apple flavored candy, I know I'm limited to this group. And of those, 23%, or 0.23 are apple and round. So the probability of the answer to this question is 0.23 divided by 0.42. Okay? If this is all the candies, if this box represents all the candies, okay? And let's say, you know, this is the apple, right? So 0.42, this is the apple section, and this is the cherry section, and this is the strawberry section, okay? And of the apple flavored candies, I'm drawing kind of a line. So 42 represents this entire, like if I've got a drawer of candies, right? This represents the entire, all the apples is 42, and of those, 0.23 are round. These are the candies that are apple and round, yeah? Apple and round. So if I'm limited to just this section, okay? If I say, go into the drawer, but you're only allowed to draw from the apple flavored section, what's the probability that you're going to get a round flavored candy? 0.548, okay? Because you're limited to this section, which has 42% of the candies, and 0.23 of that 0.42 is round. Does that make sense?
Okay.
Okay, so symbolically, okay, and this is important that we know how to do this symbolically. We write, this is the probability of drawing a round candy, and you're going to see this vertical bar, which means given it's apple flavored. Okay. This is the probability of drawing a round candy, vertical bar meaning given, if we know that it's apple flavored. Okay, so this is read as round given apple. And what does that mean? We know that it's apple flavored. What's the probability that it's also round? Okay, so the probability that something is round given that it's apple flavored is equal to the probability of round and apple divided by what? Probability of being apple flavored candy. Okay. And then here I got probability 0.60 of all candies around, right? Okay, so notice this thing is very different. It looks similar. But it's very different. Oops. Okay. What's this answer? So do we have a number? What is the question here?
What's the probability of that?
What's the probability that a candy is apple flavored given that it's round? So what does that mean? That means if you go to the the box of candies and we say, okay, now you're limited to the round section. Okay, you're just limited to the round candies. You're not allowed to have any square candies. Okay? So you're limited to just the round candies, and you're going to draw one at random. What's the probability that the candy you get is apple flavored? Does that make sense? That's what we're asking here. So this is probability of what? Apple and round divided by probability of getting a round candy. Okay? So apple and round, 0.23 divided by probability of a round candy, 0.60, 0.3833. Yes?
Could you quickly explain once again the difference of and given, or is it? That's it.
So given says we're limiting ourselves to just these types. So I'm asking, if we're limiting ourselves just to this type, what's the probability that that it's an apple flavored candy? Okay. So for example, okay, if I pick a random person in the United States, what's the probability that this person is male? Just
48%.
okay, about 50%. Okay, so if I pick a random person in the United States, in the United States is about 50-50 male female. So we'll say 50% chance that this person is male. Okay. If I pick a random person in the United States and I say, what's the probability that this person watches ESPN every day? No. In the United States, how many people? Let's say ESPN has excellent viewership, and let's say 6% of Americans watch ESPN every single day. Okay, these are unreal numbers for any cable news network. Okay, by the way. All right. Now, if I tell you I picked a random person and this person watches ESPN every day, what's the probability that this person is male?
95.
Huh? It's probably going to be like 90%, okay? 90%, all right? Just because ESPN's viewership is predominantly male. Okay, we all know what ESPN is, right? It's like the sports channel. Okay. Huh? What's that? Okay. So you're thinking, if we think about this, okay? This is all of America, all right? Let's just say this is all of America. All right. Now, half are male and half are female. Okay, so 50% male. Okay, let's just let's just simplify it. Let's say there's only males and females in the United States. Okay. All right. Now, somewhere in here, 6%. So just this little chunk here. This entire box represents 6%. Okay? These people watch ESPN. Okay? Now let's say if 0.054 is in the male, so this is, what's the probability that someone is male if we know that they watch ESPN all the time? Let's say that's 90%, okay? Now some women do watch ESPN every day, but not as many, okay? Not as many. This is a very different question from what's the probability that somebody watches ESPN and is male, right? If we pick a random American, what's the probability that this person happens to watch ESPN every day and is male? It's not 90%, right? It's like, it's 0.054. Okay, can we see the difference here?
Thank you.
Okay.
The PR mail instead, can we just kind of add the words to the
So, if someone watches ESPN daily, what is the probability this person is male? Okay. Got a lot. Okay, let me talk about sequences of events. And then we also have to talk about checking for independence. Okay? Sequences of independent events. independent means the outcome of one event does not influence the outcome of the other event. So rolling a die is an independent event. Or if I roll a die multiple times, each roll is independent of the other rolls. Okay? Just because I rolled a 6 doesn't make the 6 any more or less likely to roll again in the future. If I flip a coin, each coin flip is independent of the next coin flip. Does that make sense? Okay, so let's say, what is the probability of rolling a 5? What's the answer there? Rolling a die.
1 out of 6.
1 out of 6. Okay. What is the probability of not rolling a 5? 5 out of 6. Okay. If I roll the die twice, what is the probability I see 5 and then 5? Okay, so here, the probability that I see a 5 on the first die is what? 1 out of 6, okay? And then, if I roll it again, what's the probability that I see another 5 on the next one? 1 out of 6, okay? So this gives me 1 out of 36. Okay, so I could ask this thing, another way I could ask it is, if I roll a die twice, what's the probability I see 2 5s, right? And the answer there is 1 out of 6 times 1 out of 6. 1 out of 36. Are we okay with this? This is just the same question reworded in a different way. Okay, if I roll a die twice, what's the probability I see no 5s? 25 out of 36. Probability of not a 5 on the first die roll is 5 out of 6. Probability of not a 5 on the second one is also 5 out of 6. When I multiply these together, I get 25 out of 36. Okay.
Can you leave it as a fraction?
Yeah, you could leave it as a fraction. Fractions and decimals are the same thing. You guys realize this, right?
Yeah.
Okay? It's just representing a number. It's just a number. Okay. If I roll a die 3 times, what is the probability I see no 5s?
One
125 out of 216. 5 out of 6 times 5 out of 6 times 5 out of 6, right? 125 out of 216, okay? And you get some kind of decimal here. Is this okay? Alright. If I roll a die 3 times, what is the probability I see at least 1 5? No? Seeing at least 1 5. How's this going to happen? So I could see the first one could be a 5, the second one could be a 5, the third one can be a 5. I could see 2 5s, I can see 3 5s. There's all sorts of things that could happen, right? That qualify as seeing at least 1 5. What's the only time I don't see at least 1 5?
1 out of.
You guys are making it more complicated. When's the only time, if I roll a die 3 times, what's the only way I won't see at least 1 5?
125 over 216.
What has to happen for me to see, for me not to see at least 1 5? No 5s. No 5s. Okay? So the only way I don't see at least 1 5 is if I get no 5s, which means at least 1 5 is the complement of
No 5.
no 5s, right? Does that make sense?
Yes.
Okay, so at least 1 5 is the complement of no 5s. Okay, so what is the probability I see at least 1 5 then? One minus 125 out of 216. Right? This is the complement, this is the probability I see no 5s. So the complement is 1 minus that. So what is this? This is 91 out of 216. Is this working?
Is it 1
Study, when you guys do your homework this week, please pay very careful attention to the different problems you guys encounter, okay? Alright, let's try, are 2 events independent? This is the question. Okay. Okay. How many people in the world?
280.
Oh.
Okay, let's say 7 billion, okay? How many people live in China? Okay, let's just keep things simple, okay?
1.5.
Let's say 1.3 billion in China. Or no, let's make it easier. 1.4 billion in China. This is that's not quite accurate, but this number's too big. But this will make our math easier. Okay? And this is not quite correct because there's distinct languages, distinct Chinese languages. But let's say we just grouped all these Chinese languages together and we said 1.8 billion people speak Chinese. Okay, so what is if we pick a person at random, what's the probability that this person is from China? What's that? Yeah, 1.4 divided by 7, which is 0.2. Okay? 20% chance that this person is from China. Okay. If I pick a person at random, what's the probability that this person speaks Chinese? One 1.8 divided by 7, and what's that? It's a little bit tougher. 0.26, okay. Okay. Is being from China and speaking Chinese, are they independent? What is the definition of independent again? One does not influence the other. Okay. So, the way you imagine this is, if I tell you I picked a person at random, and this person is from China, okay? What is the probability that this person speaks Chinese? Very high, okay? So how would I write that? I would say the probability that this person speaks Chinese, given this person is from China, is very high, okay? Probably like 99%, okay? Or very high. Okay? They are not independent. Knowing the fact that this person is from China influences our answer about whether someone speaks Chinese or not, okay? I mean, this number is, again, ridiculously wrong, but if I just said I've picked a random person from around the world, what's the probability that this person speaks Chinese or knows a little bit of Chinese? Your answer would be 0.26, maybe 1 in 4, okay? 1 in 4 people maybe know Chinese. But then, once you know that this person is from China, now it's not just 1 in 4, it's like 99, almost 100% that this person can speak Chinese, right? Okay, so the key here is that the probability that someone speaks Chinese, okay, if we know nothing else about the person, that's what this thing represents. The probability that someone speaks Chinese, if we know nothing about the person, is 0.26, and that does not equal the probability that this person speaks Chinese if we know they are from China. Okay? Does not equal 0.99. Does that make sense? So they are not independent. So the probability that the event that somebody speaks Chinese and the event that someone is from China, they are not independent events, because the fact that we know someone is from China changes the probability that they speak Chinese. Okay? So once we know someone's from China, then we say, oh, the probability they speak Chinese is super high. Whereas when we knew nothing about that person, which is what this represents, the probability that this person speaks Chinese in of itself is only 0.26.
Is
Yes?
this the same as correlation is not equal causation?
It is not the same thing as that, because correlation only works for quantitative variables or numeric variables, and speaking Chinese or not Chinese is what? That's a categorical variable, right? So all of our probability things so far we're only learning categorical things. Okay, so there's certain things that feel familiar and similar, but they are distinct concepts. Okay, let's try something else. Okay, let's say the probability that someone likes ice cream. Let's say 90% of people like ice cream. Okay, let's say the probability that someone is male is 50%. Okay, and I'm going to ask, is being male independent from liking ice cream? Okay, well let's check. Okay, well for being male to be independent of liking ice cream, what percentage of males must like ice cream? What must this number be? What is this? So if we know someone is male, that's what this is saying, right? So if I pick a random person and I know that this person is male, what's the probability that this person likes ice cream? 40? No, okay. Think about this. If I pick a person at random, okay, stop trying to do math here. I'm picking a person at random. What's the probability that this person likes ice cream? 90%, 0.9. I pick a person at random. What's the probability this person likes ice cream? 0.9. Okay? Now I'm going to tell you something about this person. This person is a guy. It's a man. What's the probability that this person, that he likes ice cream now? 0.9. Okay, why would, huh? If I picked a random person, and the probability that this random person likes ice cream is 0.9, why would knowing that this person is male suddenly change that the probability that this person liking ice cream? Does that make sense? Okay? I mean, if I said, if I picked a random person and I said, okay, what's the probability that this random person likes ice cream? You say 0.9. Now I tell you, oh, let me tell you something about this person. This person's lactose intolerant. What's the probability that this person likes ice cream? Okay, it's a lot lower, right? Maybe it's like 40% or 20%, right? They actually like ice cream, but they can't eat it, and their life sucks. Okay? Who knows, right? But it's probably going to be 0.9. I mean, not 0.9. But knowing that someone is a male shouldn't influence the probability that this person likes ice cream. So this thing is 0.9 also. Okay? So they are independent. Ice cream and male are independent. Because probability of liking ice cream is equal to the probability of liking ice cream, even if we know that this person is male. Okay, does that make sense? Alright, so let's try this concept again. If I pick a random person, what's the probability that this person is male? 50%, okay? Now I'm going to tell you something. This person happens to like ice cream. Okay? Do you want to change your answer?
No.
What's the probability that this person's male? 50%, okay? So 90% of males like ice cream, and 50% of ice cream lovers are male. Okay? So how would I write that? Probability of male, which is 50%, should equal probability of what? Male given likes ice cream. Okay? Can we get these numbers from a table? Do we know how to do that? Yeah? No? I know it's 10 o'clock, and if you gotta leave, you gotta leave. But let me just, I just want to put something in a table and make sure we really understand this, okay? Male, female. Ice cream does not like ice cream. Okay? Let's say there's just 100 people total. From here, we can see probability of being male given ice cream. What is this probability? How do I get this from the table? What is the number?
45.
Huh? Probability of male given ice cream. 45 out of what? Out of 90. Out of 90. Because we know, right? You review your notes, okay? Probability of male given ice cream is equal to probability of male and ice cream divided by probability of ice cream. So this is going to be 45 out of 90. Okay, so 45 out of 90 is 0.5. What's the probability of being male? Huh? 50 out of 100. 50 out of 100. 0.5. So probability of male given ice cream is equal to the probability of being male. Okay? So you have to, go through your notes, do the homework, okay, nice and slowly, and make sure you understand everything that you're doing. Okay? If you don't understand something in the homework, review it until you get it. Watch these videos and make sure. You got to be comfortable dealing with a table and getting these types of numbers. And you got to be comfortable checking if things are independent. Okay? You guys have some homework. We'll have a quiz next week.
So chapter 4 on this?
Quizzes on chapters 4 and 5. Again, I have a list of the things you need to know for the quiz.